This is part 2 of the Chapter 3 homework solutions for Physics 102A at Porterville College. We pick up with number 63, a baseball hit above the ground leaves the bat 27 meters per second at an angle of 45 degrees. And we need to find how far does it go, how much time in the air, what is its maximum height. Part A is very easy to do with the range equation. You have V naught. You know sine 2 theta, you know g, so plug all those things in and you can get 74.4 meters. Now, if you didn't have the range equation or you didn't think to use it, you would probably do part B before getting to the answer to part A. So let's go on to part B and see how we would solve for the range if we didn't know the range equation. We need to find the time in the air, and that's what part B is asking for. So first we need to evaluate the vertical motion. V naught y is 27 meters per second times the sine of the angle. So original velocity is 19.092 meters per second. If we want to know the total time in the air, let's evaluate this when the velocity is equal to the negative of the original velocity in the y direction. So here I've taken this kinematic equation, and notice I've replaced Vy with negative V naught y, because that's when it'll hit the ground, when its velocity in the y direction is the opposite of its launch velocity. Then I can solve for time, 2 V naught y over g, and I get its time in the air as 3.896 seconds. Now, to go back and solve part A, now we can just say its distance that it goes is V naught x times t. V naught x is V naught times cosine theta t, or V naught times cosine theta naught. Then multiply that by t. So you can plug in those numbers and get the answer that we got in part A. Part C asks about its maximum height. For its maximum height, remember that's where y velocity is equal to 0. So I take this equation right here, and I'm going to make, or let's solve it for delta y. Notice I've made Vy equal to 0. So we get delta y is negative V naught y squared over negative 2g. So we plug in those numbers and get a maximum height of 18.6 meters. '65 has a ball rolling off the table. I want you to look at my diagram and see the conventions that I've set up to do this problem. First of all, we have the origin at 0, 0. I've drawn here my coordinate axis, my coordinate system. I've made the positive y direction go down. So distance, x, when it hits the ground is 0.15 meters. V naught is equal to V naught x because its angle that it was going was 0 degrees. All of its motion when it was rolling off the table until it actually left the table was in a horizontal direction. So V naught is equal to V naught x. Part A says find t. Well, we can use this equation. T is equal to x over V naught x. So you plug in those numbers and you get half a second. And actually, I see for part A, it's asking what is the vertical drop, how high is the table. So now that we know t of 1/2 second, use this equation. Y equals, a couple of things go to 0, and we're left with y equals 1/2 g times t squared. And acceleration is positive because up here I've made y, the positive y direction, go downward. So there's no negative sign here. And we get y equals 1.225 meters. Question B is then asking, what if you have same tabletop, but ball going faster? Okay, so recognize, if it's the same vertical drop, it's going to fall in the same time. And so we just have a different time of flight. X equals V naught x times t, so we fill in the new V naught x, 0.6 meters per second, times the same time of 0.5 seconds, and so it'll go twice the distance, 0.30 meters. So going twice as fast will give it twice the distance before it hits the ground. Number 71, you can use the range equation for this. It's asking about a minimum speed. Keep in mind, to get a certain range, the minimum speed that you can get that range will be at the maximum angle. So maximum angle being actually maximum sine of the angle. The angle is 45 degrees. That's how you get max range. So sine of 2 theta will go to 1. So we're left with range is v naught squared over g. V naught then is square root of range times g. Plug in those numbers and you get 383.4 meters per second. To find the time in flight, time is that distance over the horizontal velocity. So I've plugged in range over v naught cosine theta naught, where range is 15,000 meters, v naught is what we found in the first part, and the angle is still 45 degrees, and you should get 55.3 seconds. Number 85 involves subatomic particles going around a circular path. So we have the radius of 1200 meters, we have speed, it says close to the speed of light, so we'll just go with 3 times 10 to the 8th meters per second. We're going to relate this to velocity, and here we have period is 2 pi r over v. And so we plug in those numbers. The period is 2 pi times the radius of 1200 meters divided by 3 times 10 to the 8th meters per second. And we get 2.5 times 10 to the negative 5 seconds. Part B then asks, what is the radial acceleration, or the centripetal acceleration? That's v squared over r for anything going around in a circle. Well, we've got v, we've got r, plug those numbers in, and you get an extremely large acceleration of 7.5 times 10 to the 13th meters per second squared. The last one for chapter 3 is number 89. We have a radius of 12,000 meters on the surface of this neutron star. We have time, or the period of 1 second. We need to find the acceleration. Well, in order to find acceleration, we need v. So remember, v is 2 pi r over t. And now we're going to plug into the radial acceleration formula. Radial acceleration is v squared over r. Here I've got v, 2 pi r over t. I've substituted, then you square it. And remember, it's divided by r, so here I've got the times 1 over r. When you put all those together, you've got acceleration is 4 pi squared r over t squared. Plug in the values, and we get radial acceleration on the surface of this neutron star is 4.7 times 10 to the 5th meters per second squared.